Yay!
Yay! All right, our first example of forces as vectors is going to be a pretty typical statics problem. Suppose I have a mass and it's just hanging from a couple of cables to the ceiling up top, and maybe the cables make different angles with the ceiling. So what we're going to do is, we know already, right, that there's going to be a downward force on the mass, and this is just going to be mg. And what we're going to do, what we're after, is to try to figure out what the tensions are, T1 and T2, the tensions in the cable. And right away you might be thinking, wait, doesn't tension run both directions? Like where the cable attaches to the ceiling, there's a tension running the opposite direction, right? But what we're interested in is not the force on the ceiling. We want to sum together all the forces that are on that mass. And that's how we're going to solve for T1 and T2. So always put yourself in the position of the mass. What does the mass feel? The mass, if you were the mass, you're going to feel gravity pulling down, and then you would feel each of those tensions pulling up on you to balance, right? So what we're going to do is write down Newton's second law. And Newton's second law is you sum all the forces together on an object, all the vectors. We sum all the forces together, and the vocabulary is important. We sum the forces together, and then we set it equal to its mass times how it accelerates. I'm trying to say that carefully. The sum of the forces on the left is equal to the mass times how it accelerates on the right. That'll become important as we go along when things accelerate weirdly. But for now, it's going to be pretty easy because this thing's not moving. It's just hanging there. So A is going to be 0, right, in this case. But anyway, that's the general prescription. So this means that it's a vector equation. And remember, a vector equation holds in the x and the y directions. So it ought to be true that if I sum all the x components up, this equals max, right? And then if I sum all the y components, this should equal may. So both of those should hold. And I mean, that's what we're going to do. So, okay, in the x direction, let's write it down. In the x direction, what do I have? I got T1 has a little bit of an x component going to the left, right? So it's going to be minus T1, and that component is going to be cosine 60 because, right, if you like thinking about the horizontal angles, just draw a parallel to the ceiling. So that's going to be 40, right? That's the same angle as 40. And then this is the same angle as 60. So this works. So T1 cosine 60, that's the x component heading back to the left. And then I got a T2 cosine 40, that's going to the right. And in the x direction, that nothing's happening, A is 0. So this is just going to equal 0. Cool. And now all we have to do is do the same thing for the y. So sum the forces in the y direction. Let's see. I'm going to have T1 is pointed up. So this is going to be T1 sine 60. T2 is pointed up. T2 sine 40. And then I got mg down, right? So it's minus mg equals 0. But can I just really quick scoot the mg over to the other side? Can I just do that? So add mg to the other side, and so we get that. Very cool. That's all there is to the physics. Right now, in deference to the mathematicians, it's just algebra. So there's 2 equations and 2 unknowns. I don't know T1 and T2, but I have 2 equations. So one strategy is that I can go ahead and just solve. Maybe I'll solve the top one for T1 and then plug it into the bottom one. So I'll solve the top one for T1 and plug it down in there. So T1, what's T1 going to be? It's going to be T2 cosine 40 divided by cosine 60. You might, I mean, maybe if you haven't done much of this yet, you might want to go ahead and plug in what cosine of 60 is right away. But that just makes me nervous. That's just a whole bunch of ugly looking decimals. I don't really like the look of it. So I try not to plug in numbers until the very end. on most things. Okay, so that's going to be T1. So now I just stick it down in the second equation. So let's see, that's going to be T1 is T2 cosine 40 over cosine 60, and then I still have a sine 60 up top. And then I got my T2 plus T2 sine 40 equals mg. Oh, I didn't tell you what m was, right? Let's just say m is 100, kind of a standard big mass, 100 kilogram. Okay. So now we're ready. Now we can solve. Now we can solve for T2. So let's see. I did some of these ahead of time. T2 times. Oh, if you plug that mess in to your calculator, what did I get? I got like a 1.33. I rounded a little bit. Don't care. And then T2 plus T2. This was like, what did I get? 0.64. This is the stuff that you can do and see if you can duplicate it. It's not very interesting, right? It's just calculator work. So this is equal to mg. Look, though, 1.33 plus 0.64, what's that? That's like 2. It's really close to 2. Let's just call it 2 because I don't care. So 2 T2 is mg. Mg, as is going to be our usual thing, we're going to call g equal to 10 because, again, don't care. Close enough. Right? If you want to exactly match an answer in the back of the book, or if you're trying to be really precise for a lab, or for heaven's sakes, if you're making a bridge or whatever, sure, G is 9.81, whatever. But I mean, if we're just trying to get a handle on the physics, let's just say G is 10. That's fine. So mg is going to be like 1,000. And then we said the 1.33.6, that's like 2. So T2 is 1,000, and then I'm going to bring the 2 over, divided by 2. That's like 500. 500 newtons. Cool. And then I can go back and solve for T1. So T1 is 500. There we go. Let's get to where you can see the whole screen. 500 times cosine of 40 over cosine of 60. Let's see. And when I did that, what did I get? This is not the interesting part. What I got? 766. Okay. So these are the two tensions in the cable. And so this is what it will take to hold up that mass. Notice, I mean, the kind of the interesting thing about this example is that if you look at those and you add them up, that's what 1,266 newtons. That's more than the thing weighs. So it takes more in tension than the thing weighs because they're at an angle. We'll see this as we go along. That probably the cheapest way in terms of newtons that you can do it is just to hang it directly from the ceiling straight down. But if there's any kind of an angle involved, then it turns out that the tensions get larger. And we'll see an interesting example that kind of maximizes that later. All right, so this example is kind of a typical thing you'll find in statics where you might have a couple equations, 2 equations and 2 unknowns. Maybe you have to solve for tensions in cables, and the object is static. So this is sort of a standard example of those. So next time we'll start talking about things like blocks on planes and dynamics where things are actually moving. So that maybe that's a little bit more interesting.